Okay, I want to explain perfect square trinomials here. So what we're going to do is we're going to start backwards in like a factored form and work towards standard form so we can see this pattern. So let's just take a simple example of a perfect square trinomial. Oops. And look at x plus 1 quantity squared. Now, if we were going to write this out fully, anything squared is just multiplied by itself. So we would look at x plus 1 times quantity x plus 1. And we can write this in standard form by using the FOIL method. So the first terms, x times x is x squared. The outer terms would be x times 1, which is x. The inner terms, 1 times x, which is also x. And then the last terms, 1 times 1 is 1. And we can combine like terms. So x plus x is 2x. We get x squared plus 2x plus 1. Now you're not going to see the pattern until we do a few more. So let's look at the next simplest example, which would be x plus 2 quantity squared, and we'll do the same thing. So we'll do x plus 2 times x plus 2. I'm going to FOIL this. I'm going to do this a little bit quicker. So we have x squared plus 2x plus 2x plus 4. And if we combine like terms, we get x squared plus 4x plus 4. I'm going to keep going, and we'll look at x plus 3 quantity squared, which would give us x plus 3 times x plus 3, and that gives us x squared plus 6x plus 9. And let's look at one more. So if we have x plus 4 quantity squared, that gives us x plus 4 times x plus 4. And if you were to FOIL that, you would get x squared plus 8x plus 16. Okay, so I'm going to scroll down because I typed these out, and so we can look at this pattern. But again, all I did is I took a quantity like x plus 1 and I squared it. So we're just multiplying it by itself. Okay, so these are the 4 examples I did written out. And what you should start to notice is there's a pattern. And you might say, okay, these are increasing by a factor or by 2x. And these are all perfect squares. And if you look, the first term in each of these is just the first term in parentheses squared. And the last term here is just the second term in parentheses squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. The middle term is if you took the first term, multiplied it by the second term. So in this case, we would have 1x, and then we multiply that 1x term by 2. The middle term, we take the first term and second term and multiply them, so 2x, and then multiply that by 2, and you get 4x. Here, 1x times 2 is 2x. 2x times 2 is 4x. Here, we take the first term and multiply it by the second term, so that's 3 and x, and multiply it by 2, and you get 6x. And I think you're starting to see the pattern. Here we take x times 4, so 4x, and we multiply it by 2, and you end up getting 8x. And so we can write a general rule for this. So if you have a perfect square here, so you square a binomial just has 2 terms. So you take a plus b, that quantity squared, you end up getting the first term squared, so a squared, the last term squared, b squared, and then twice the product of the first and last term. So take a times b and multiply it by 2. Where this becomes convenient is if you get more complex binomials squared. So here we can apply this rule. So if we apply this rule, we should just be able to square the first term. So that would be 4x squared. We should be able to square the second term, 7 squared. And then this should be 2 times the first term, 4x, times the second term, which is 7. So 4x times 7 is 28x. So 2 times 28x is equal to 56x. So filling in this term is just 56x. And then if we write this out, if we have to distribute this exponent across the parentheses, you have to square each term. So 4 squared is 16. X squared is x squared plus 56x, and then 7 squared is 49. So this is our squared binomial written in standard form. And so what you're looking for when you're going to apply this rule, and again, we're going to look at it going backwards, what you're looking for is a perfect square for A. So A, or your first term, is a perfect square. And what I mean by that is if you take the square root of this number here, you're going to get a whole number. So the square root of 16 is 4. And you're looking for the last term. To be a perfect square. And again, I'm looking for a number where if I take the square root of it, it's going to be a whole number. So I'll quickly list those for you. You have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. You have 121, 144. They're not going to go much higher than that. So when might this be useful? Well, let's take a look at this expression. So 36x squared plus 132x plus 121. Now, just looking off the bat, do these have any common factors? I don't think so. And so you can use the method we talked about where we do a times c. And if you do a times c, you end up getting 4,356. So here I would have to find factors of 4,356 that add to 132. Is this possible? Yeah, of course. Is this convenient? No. That's going to take you a long time to figure out. But what you can recognize, and I'm going to erase all of this, what you can recognize is that your first term here is a perfect square. So square root of 36 is 6. Square root of x squared is x. So you can write that as 6x quantity squared. The second term, 121, is a perfect square. Square root of 121 is 11. So the next thing you have to ask yourself is this term inside the parentheses 2 times 6x times 11, is that equal to 132x? So 6x times 11 is 66x. And 66 times 2 is 132x. So I have a perfect square trinomial. And so then I can just apply the rule and say, this is A, this is B, and so the factored form is A plus B quantity squared. And so these are equivalent, and this is our factored form. You can check if your factoring is correct using your calculator. And the way you do that is I'm going to type this into my y equals, my original expression, 36x squared plus 132x plus 121. So I'm going to go to y equals, and I'm going to type my original expression. So 36x squared plus 132x plus 121. In my second y equals, I'm going to type my factored form, so 6x plus 11 quantity squared. 6x plus 11 quantity squared. And then I'm going to go to my table. If these are truly equivalent, then all of the numbers should be the same, and they are. And so that's how I know I'm right, is that for every x value, the y values are the same. So those expressions are identical. So again, you can type your original expression into your y equals. You can type your factored expression into your y equals. Go to your table, and then you can check to make sure that all the numbers line up. Okay, one more example. So our first term is a perfect square. Square root of 49 is 7. Square root of x squared is x. And our last term is a perfect square. Now, don't forget that 1 is a perfect square. Square root of 1 is 1. So we just have to make sure that our middle term is the product of the first and the last terms times 2. So we would do 2 times 7x times 1, which is equal to 2 times 7x, which is equal to 14x. So what this is telling me is that this is a perfect square trinomial. And so the factored form, we just take the square root of the first term, so 7x, and the square root of the second term, 1. That quantity is squared. So these two expressions are equivalent. And I can check it really quick on my calculator. So I go to y equals, and I'm going to type in both expressions. So we had 49x, whoops. Here we go, 49x squared plus 14x plus 1. And then that turned into 7x plus 1 quantity squared. If I go to my table, they should be equivalent, and it looks like they are. So that's how we know we wrote the right expression. Okay, we start to see a similar pattern when it's something like x minus 1 quantity squared. So we'll do the same thing. We can write x minus 1 quantity times itself, and we can FOIL it. So you get x squared minus x plus 1, which gives us x squared minus 2x plus 1. We can look at x minus 2 quantity squared, which would be x minus 2 times x minus 2. We can FOIL that, and we get x squared minus 4x plus 4. And I think you're going to start to see the pattern. X minus 3 squared gives us x squared minus 6x plus 9. And x minus 4 quantity squared gives us x squared minus 8x plus 9. So you start to see a similar pattern as when it's x plus 1, with the exception that we're subtracting the middle term. And so we can write out a generalized formula for this, for when we're subtracting inside the parentheses. And it looks like a minus b quantity squared is a squared minus 2ab plus b squared. So it's the same pattern, except we're just subtracting here instead of adding. We'll look at one example here. So here, what you should recognize is you have a perfect square for your first term. You have a perfect square for your last term. And so square root of 81 is 9. Square root of x squared is x. So it would be that quantity squared minus 180x plus 10 squared. So this would be your a term. 10 would be your b term. So over here we can do 2 times 9x times 10, which would be 2 times 90x, which would be 180x. So what you can see is this follows that pattern. So you have a perfect square trinomial here. And so the factored form would just be a, 9x, minus b, which is 10. Oops. And that quantity would be squared. So our factored form, these are equivalent.